This is Physics 2212 Lab 5, Faraday's Law. The purpose of this lab is to understand Faraday's Law and flux by comparing experimental data to computational results. Our experimental time, of course, was 1.773 seconds, which was a little bit slower than the computational time of 1.725 seconds. The fundamental principles are Lenz's law, Newton's second law, and Faraday's law, because a moving magnet will induce an EMF through its magnetic flux. The system, of course, was the magnet, and the surroundings were the aluminum tube. We assume that air drag is negligible and that we have an ideal powerful magnet. First, we drop a powerful magnet straight down into a conductive non-ferrous tube, and it falls out the other end. The prediction, of course, is that the magnet just falls down as normal, with no other factors other than air drag and gravity. Well, negligible air drag. The observation, of course, is that the magnet falls slower than normal, so there must be external forces present that slow down the magnet. The mass of the magnet, of course, is 0.025 kilograms, and the average fall time recorded was 1.773 seconds. Here's my code. The first screenshot you see here are all my inputs, and I assume that the radius is the inner radius plus the width of the foil. Next, I have to calculate the magnetic field of a dipole, and I also need to calculate the magnetic flux, because I need to use these values to then figure out what F net is. The force of gravity, which is constant, plus the force of the magnetic field, add up to make F net. Now, this also implies that F gravity and F magnetic are similar in magnitude. I also applied Newton's second law by saying that F equals ma, and I can also figure out what the position of the bar is through time, and that's how we generate the animation. Obviously, you can't see it here, but the image to the left is what whenever you run the code, it shows the magnet falling down through the tube. Here's another snippet of the code. It's just a graph that shows velocity versus time. If you notice the flat section there, that shows the moment the magnet enters the tube. How do we know that? Well, the magnitude of the velocity and or the magnitude of the forces F mag and F gravity are supposed to be the same. Whenever they're the same, they counteract each other, and the velocity remains constant. Outside of the tube, however, the forces of the magnet don't act, the magnetic forces don't act on the bar, so the velocity is non-constant. In other words, it is only affected by gravity. Now, here we're going to interpret our results. The intensity of the coloring on the tube, Lenz's law shows that the red is counterclockwise and the blue is clockwise. This is due to Lenz's law. If they match up, it goes with the right-hand rule, and if they don't, then it opposes the right-hand rule. What happens to the dynamics of the system when you flip the magnet around? Well, the current gets flipped. However, velocity is left unaffected. We ran the trial 5 times without really paying attention to the orientation of the magnet, and nothing really happened. How does the total time in tube of your real-world system compare to that of your computational system? Well, the observed results show that the magnet took a lot longer to fall in real life. So, even though we assume the air drag is negligible, it likely is not negligible. So, if we were to add more loops, then they would probably match better, but since we didn't, they don't. How does the shape of the velocity time plot? Oh, this is what I talked about earlier. The magnetic forces are equal in magnitude to the forces due to gravity. When outside the tube, the velocity is non-constant, so this implies that Newton's Newton's third law comes into place. So, what if we were to add holes or slots into the tube? How would this affect the ring currents? Well, since there's less surface area, that affects the flux. So, as a result, the magnetic force that counters gravity is less, so the magnet would fall faster. The resistivity of the conductor was reduced as close as possible to 0. How would the dynamics change? Well, since Ohm's law states that V equals IR, a decreased resistivity would mean an increase in current, so the magnet would fall slower. And of course, conclusions, we assume some user error from the stopwatch. Of course, and there was probably air drag during the descent. So that could be why the computational model and our observed results don't really match. That's about it. See ya!